Thank you very much. I have a couple of videos, so I'm going to stick close to the podium until we get through the videos, and then I'll wander a little bit. So we weren't originally an HPC software company, but we were really much very focused on graphs. And so for us, graphs are a data structure. So they're, think nodes and links or edges and vertices. And graphs show up in many, many important applications, social networks, communication networks, biological networks. Anytime that you need to represent complex dependencies in your data, graphs are a very good data structure to be able to do that. One of the challenges is that as graphs get very, very large, they become a data structure that challenges existing computational platforms. And if you look on the right-hand side of this slide, you'll see a sort of a map that you've probably seen before, which is a map of the internet circa 2006. So we started as a graph database platform. We've been around for about 10 years. We have about 700 downloads a week. Being open source, we get lots of different interesting applications and use cases ranging from Fortune 500 customers to research organizations. And we're going to talk a little bit about some of these today, but we've highlighted sort of the 5 here that we're seeing the most traction in the space. One of the biggest areas that we've seen a lot of growth in is in precision medicine. I don't usually attend conferences where people talk about precision medicine as much as I've heard it talked about today, which is really, really very exciting. There's a company in San Francisco called SciAps, which is really pioneering graph-based data integration approaches for precision medicine. And so I have a video of the SciAps CEO, Jonathan Hirsch, talking very briefly just to introduce you guys to some of the challenges in the precision medicine space. So I'm going to attempt to swap over to that now.
About a lot of the interesting technologies earlier today, the new diagnostic technologies, new biopharma drugs that are coming out. But really, when the health systems think about precision medicine, they're thinking about different issues. They're thinking about how to differentiate against competitors. They're thinking about clinical trials and getting patients on. They're thinking about the reimbursement landscape. But of course, all of these health systems face difficulties in the real-world implementation of precision medicine. So they face an uphill battle with electronic medical records and other technology that doesn't really support the real-world implementation. And what you're going to hear from is a set of panelists who work on the real-world implementation of precision medicine. And one of the challenges faced is this challenge that we all know about, which is the massive issue of the lack of visibility of genomic and molecular data in a clinical workflow. So when a physician actually wants to utilize molecular and genomic testing technology, they're often left with a fax. They're left with this beautiful genomic data that has been reduced to a piece of paper that's been sent over the transom. So this is one of the issues that we deal with today, and one of the things that we'll talk about on the panel, how to really leverage data to enable precision medicine.
So you can see some of the challenges in precision medicine. Really very much a data, hopefully we'll be back, a data integration challenge. In the case of SciAps, they're using graphs to be able to map between different data sources and provide a way for people to make unified queries against that. But what really drives us from the conventional platform that they're on today into more of an HPC context is the data scale that they're approaching now. So today, these are the top customers of SciAps have 5 to 10 billion edge graph problems. SciAps is predicting that early next year, their biggest customers will be 100 billion edge graph problems. This size of graph scale is very much a challenge for even the best-in-class graph database platforms. It really needs different and other approaches to be able to deliver the performance that they need to get out of it. Second major use case that we see in graphs is the use case of knowledge graphs. And this is a classic graph application, but this is taking different graph representations, using them to arrange information to be able to provide semantic search capabilities and other queries. And so if you look here on your left, you'll see a Google search for the largest city in Europe with a female mayor, and you get back a bunch of pages. If you ask Wikidata, you get back a couple of people. And so it's really the difference between a knowledge-based answer and just a bunch of text coming back. And so we'll talk in a little more detail today about how the research space and the British Museum are using a knowledge graph approach to be able to organize the cultural artifacts that are under the British Museum's management case. But there's also a number of other use cases there. A big space for us now here as well is chemicals and material science. And so this is cases where there's been a long-standing investment in high-quality graph data that is really paying off. And so in this case, we have a large material science company. They're using a combination of publicly available NIH data, the PubChem data set, which some of you may be familiar with, along with proprietary material science data that they have. They're using graph-based data integration approaches to be able to try and identify new compounds and facilitate their research capabilities. And we see this as a very much a growing area for graph applications. But again, the data scale is approaching a level that challenges existing platforms. And so just the core reference data these days is above 10 billion edges. When you bring in other different types of data sets, it gets even larger than that. Then they want to fuse it with proprietary internal material science data, and you just add more data to that. So it's a very much a large-scale graph challenge. So the last example here is a law enforcement application. This is looking at a call data record type scenario where you're taking sequences of events that have geotagged information. When something happens, you want to be able to draw a box around all the events and then go back and replay that in time. This is a very large-scale graph problem. Currently, the data scale is about 40 billion edges. They need to scale to be able to get to a 180-day rolling window to what we think is about a trillion edge graph. And so these are, again, very, very large graphs that are going to exceed the capabilities that we can have today with our conventional platforms. So not so much a new discussion for this group, but in many cases it is. Graphs aren't like other big data challenges. You can't just take a graph and put it into CPU RAM and expect to get good performance. And that's because graphs have these properties that they call non-locality or data-dependent parallelism. So as you traverse a very, very large graph, no matter how fast your CPU cores are, they're going to end up waiting to page in from main memory. And so we call that condition sort of the graph cache thrash, if you will, tongue-in-cheek. But if you look at this chart, across the x-axis, you see the number of access latencies per clock cycle for various different types of cache all the way up to main memory at the top. And it's very clear, looking at where you go from L3 cache to main memory, that you're paying almost a 5x penalty once you get off of the CPU cache. And so that's really why the existing CPU architectures that we're using, conventional CPU architectures, don't scale cost effectively for these kinds of graph problems. Some other things that we're looking at, and we'll talk a little bit about GPUs. We're also looking at some of the emerging capabilities with HPC systems for great interconnect speed with NVLink. We're doing some work now on some of the very early Power 8 Plus systems. In fact, we just ported our graph analytics capability to one of the Garrison boxes last week. And that's actually why it was delayed yesterday, is working on some activities related to that. So we see this as a very, very exciting area. So increased bandwidth to main memory, increased interconnect speeds, and then with the announcements at the GPU Technology Conference from last week, sort of the unified memory addressing is going to be really a game changer for us. Today, to do graph analytics on multi-GPU clusters, and we've done this on up to 64 NVIDIA K40s, you have to partition the graph and to divide the graph into the RAM available on the GPU. Unified memory addressing makes it much easier to pursue GPU, CPU hybrid strategies to be able to do that. So we think of that as a very exciting area that we see coming up over the next probably 6 to 12 months. So how do you take advantage of GPU acceleration for graphs without changing code? We've developed the capability to apply GPU acceleration for our existing graph database platform. This was based on work that originally started at DARPA under the XData program. We co-developed it with the University of Utah, the Ski Institute. It's based largely on concepts that are currently running on Titan. We also have a phase 2 SBIR with DARPA to develop the technology specifically focused for GPU accelerated graph query for cyber applications. But the main focus here, and for all our capabilities, is to really make the power of HPC and GPU acceleration available to people at a very high level of abstraction. So you're able to take the same kinds of Sparkle queries that you'll see that'll drive sort of the research space applications, add HPC GPU technologies, and experience a significant acceleration in your most data-intensive queries. So if you're into the graph database space, there's a number of different benchmarks. The Lehigh University benchmark is one of the oldest and most well-known. It's an example of a conjunctive query benchmark. They have a simulated number of universities. This is looking at a university's 1,000. Each university has students. Students take courses. Courses are taught by faculty. Faculty advise students. Query number 9, which is one of the most challenging conjunctive queries in the benchmark, essentially asks, show me all the students and faculty and courses where the student is taking the course and the faculty member also advises the student. And so if you look at this on our core graph database platform, you get about 172,000 results in about 54 seconds. And with GPU acceleration, you get the same results in under 200 milliseconds. And so the potential acceleration is substantial. This is really, you get the most benefit out of your conjunctive queries that are touching a lot of data because of that memory bandwidth advantage. We did some work recently for a defense organization looking at Spark graph traversals versus GPU acceleration. And this is looking at a 2 billion edge Twitter graph from the ICWSM paper that's been fairly well studied. And you can see in all cases, the GPU accelerated version far outperformed the native Spark graph iteration. This was using the GraphX type libraries. In the case where it was only 700 times faster, if you look at the amount of, that was on a cluster of 16 EC2 images, so you had almost 2 terabytes of physical RAM versus 192 gigabytes on the 16 K40s. So we see the speed is clearly there. The question is, how can you change your applications and build analytics to use it easily? And so this is really where we see the challenge, is how do you take this power and put it in the hands of people who understand mission, understand analytics? And so what we see the requirement as is you need to be able to write simpler and smarter algorithms that expose the power of the hardware platform, but don't require you to really drop down into doing device level optimization or specific code. So to do that, we've developed something that we call Dazzle. Dazzle is essentially designed to give you the speed of something like Apache Spark, or excuse me, the ease of something like Apache Spark with the speed that you can get out of GPUs. And I'm just going to move through these so we can make sure to talk about the use cases.
Does Dazzle stand for anything?
Dazzle does, actually. Dazzle is quite a huge mouthful here. So it's a domain-specific language for graphs with accelerated Scala using linear algebra. And so what Dazzle does is it's a DSL, or domain-specific language. It exposes linear algebra primitives through Scala, and so you're able to express graph algorithms and graph analytics in Scala, and then we compile that down into CUDA kernels, execute them on multi-GPU clusters for you. We also support user-defined functions written in Scala. Those get code-generated and also compiled into CUDA kernels. So you can stay in the Apache Spark layer, but take advantage of the performance that you get on the GPU. The second part that's very important that we've found is it's really not just enough to be really fast. on the analytics, you also have to think about how you get data to and from the systems. And so for that, we've integrated with the Spark and Hadoop ecosystems. And so if you can get your data into some kind of data frame concept through Spark or Pandas or something like that, we provide the tools to be able to help you to bring that into the GPU cluster. And we see that as very important because when you operationalize these kinds of technologies, you need to be able to look at the end-to-end analytic runtime and cycle. And so these are examples, I'll just flip through these. These are examples of the kinds of algorithms that you can write at a high level in Scala using Dazzle and be able to then execute on GPU clusters. And so what's very interesting here is we've seen a lot of blending between traditional graph analytics and machine learning capabilities. So if you start over here on the left, you see all of your things that you would expect, your triangle counting, kinds of things that Facebook does, community detection, so your Louvain, your Jacquard type things. But if you move over to the right, you see things that you might think of more of in a machine learning context, and so clustering activities, those kinds of things. We really see a lot of applications now where people are building graphs from their event data, their transaction data, they're doing machine learning over it, they're adding attributes back to the graph, they're doing more graph analytics. And so this is really designed to be able to allow people to do that at a high level and take advantage of the hardware capabilities. So Research Space is an organization that is part of the Mellon Foundation and in conjunction with the British Museum. And their mission is to deploy graphs, in this case knowledge graphs, to be able to allow people to access the cultural artifacts and cultural heritage that's managed not only by the British Museum, but by other associated organizations. And what's really fascinating about them is I think there's a number of different cultural heritage initiatives, but they're really, I think, at the forefront of applying this sort of knowledge graph based approach. And so they're working on building very, very rich navigational experiences where all of the different artifacts are well described. They're integrating things like virtual reality. There's a very rich and robust linking across artifacts, and so you could go from an artifact to the particular author or the creator and be able to explore it in that way. So it's a very interesting graph application, and it's certainly one that has a data scale that's going to increase quite substantially. This is a look at the technology stack that is being used in Research Space. And you can see it's just really a broad range of different types of capabilities. So, starting from the bottom, they have all of the different data source problems. There's analogs, of course, to the precision medicine domain, where the data's dirty. You need to do lots of semantic alignment type activities to be able to make sense of it. They bring it into some sort of data persistence tier. And then there's a number of different widgets and navigational capabilities that they provide on top of that. And so this is an example of something that the user would see when they're browsing it. And so this is a particular artifact, and you can see that they've integrated in a nice, easy to display, structured way the various different pieces of information about that. The things that are highlighted there in red represent hyperlinks, and so you can actually then follow that link in the graph from that particular item into another definition. And it's, as it turns out, it's a very nice representation of how to take all of these different artifacts, only a small fraction of which can be physically displayed to the public at any given time, and make them accessible to a much broader audience. This is just sort of, I guess, we started off earlier having an eye chart. This is sort of my eye chart. But really what it's showing is the number of different types of issues that are encountered in terms of trying to take the data and to link it together coherently to be able to provide a good navigational experience and for people to be able to access the different cultural artifacts. And I have some screenshots here, but at my own risk, I'm going to try a second video and show you guys somebody actually navigating through the research space British Museum application.
Here, for example, type paper. If I start typing paper, I will get auto suggestions, and here, this is the concept that I'm interested in, the concept paper. You see a search result here now. This is also complemented with faceted search. We can explore this result set through faceted search and exploration. So, for example, actors that these objects have met, types again. So these facets are dynamically calculated based on the given result set. But let's say I want to further refine this query by saying, okay, I'm actually interested in things of type paper from a particular period. For example, objects that have been created in the period from, let's say, 1600 to 1800. Yeah? So this will be the result set of interest now. So we see some objects here. And I may now want to, for example, search this particular, save this particular search definition for later use. So let me just save this definition. This search will now be on the clipboard, and we'll come back to this in just a minute. Yeah. So for now, let's just save.
All right, so I'll go back to the presentation. So you can see that this kind of approach enables people to access and reach different types of artifacts in a way that you just wouldn't be able to do from a physical visit. And so what he was getting into at the very end is there was also a collaboration aspect here where you can save your graph queries and be able to build up things that you can share and collaborate on with other folks. And so that's essentially, in terms of what we wanted to show from the British Museum case. The other use case, I only have a moment left here, is one that I wanted to bring up in terms of something that we're doing related to this morning's presentation on cyber. Cyber is probably, outside of life sciences, the biggest space that we're seeing growing at the moment. It's both in the commercial space as well as in the defense space. This particular example is looking at NetFlow data analysis. So I suspect many of you are familiar with NetFlow. NetFlow was originally put out by Cisco and is now sort of a more general term, and it refers to incoming and outgoing connections from a boundary of your network. Analyzing NetFlow is a very key to detecting low and slow or automated persistent threats that you have in the cyberspace. It's very easy to look at these things as graphs. Graph analytics that are interesting on NetFlow include sort of your usual suspects of traversal algorithms, ranking, clustering, community detection type things. They're challenging because they get very big. And just an hour of NetFlow can be 100 million records. If you're looking at an organization's traffic over a period of weeks or months, it's even larger than that. So this is clearly a very large graph challenge. I'll just flip through. This is an example of, I talked about the Dazzle, the Scala language earlier. This is an example of a single source shortest path algorithm written in Scala. So this runs at the same speed as our hand-tuned CUDA code. But you can see it's only a few lines of a very high-level language. And then, just as an example, the sort of general use case here, and this is something that we're doing for a large consulting firm, is taking the large GPU clusters, running graph analytics, and finding smaller, sort of around million-sized sets that can be visualized in tools for the analysts and end users. This is a tool called Graphistry, which is not our tool, but is another one. Here we're looking at, we've run PageRank over 140 million NetFlow events, and the colors represent different types of traffic. We've identified some ICMP traffic on these nodes with a high PageRank value. We're sort of drilled down on it and then expand the node to be able to look at, this is actually ICMP packets, And so we expand from that node to look at who it's communicating with. And as it turns out, and I apologize for the somewhat abbreviated example, what we're able to do here is actually find an instance of an exfiltration node. So this was a long-standing compromise in the network that using this approach we were able to reveal from an analyst perspective. So thank you very much for the opportunity, and if there's any time, I'm happy to take some questions, but appreciate the opportunity.